All right, welcome back, guys. We're on problem I, going over the possibilities for the free response number 4. I is going to be a flashcard one. I hate to do this to you again, but kind of a tricky problem. Involves this diamond silver chloride as a complex ion. Just memorize it again, make the flashcard for this one. 99.999 times 10 to the 23rd chance, and I'm not going to ask you this on the test, but greater chance of doing well in the actual AP test if you have the obscure ones memorized. J, a concentrated solution of ammonia is added to a suspension of zinc hydroxide. Now, you don't need to, again, this is going to be another flashcard one, but I want to go through this anyway because it does form something that's pretty interesting. Ammonia is NH3, and you're adding that to a suspension of zinc hydroxide. Suspensions are solids, so this is going to be zinc hydroxide. Now this makes a really convoluted ion. It's a complex ion that actually looks like this. Zn, we got these ammonias complexed in here, 2 plus 2 OH minus. This thing, whenever you see really funky things like that, that's called a complex ion. Now, it's a good thing to be able to recognize, and I just wanted to show that to you there. It asks you what are the possible geometries for this complex ion. Basically, I'm doing this because complex ions can only have a couple geometries. They're either tetrahedral, or in this case, they're square planar. And these are things we've seen before in our geometries, and I just wanted to bring these words back to you. Tetrahedrals always, have 4 things attached, no lone pairs. Square planars are going to have 4 things attached, and they're going to have 2 lone pairs. This is sp3, and this is sp3d2. So just a chance for us to talk about those words again. I thought that would be nice. Going on to K, excess concentrated sodium hydroxide. It's in water. It's a strong base, Na plus OH minus, is added to solid aluminum hydroxide. Solid, so it's going to stay apart. It's going to stay together. We see ions, so we are going to connect and cancel. Again, little tricky here. I'm not even quite sure here. I want you guys to make a flashcard on this one also. Again, I'm probably not going to ask you that. You notice how the answer forms a complex ion. They want to give you the name for this complex ion. The complex ion that you form, in this case, the overall reaction, who cares? We're not even going to talk about it. Make a flashcard for this one. It's ridiculous. All right. I, solid ammonium carbonate is heated. Okay, everything's going to stay together. Ammonium carbonate is heated. Now remember, when you heat things, it's different than burning them. Heating causes things to decompose. So we look at the cheat sheet, talk about what happens when you heat carbonates. What we're going to do is we're going to break it up into the most logical 3 or 2 things that we have here. We have N's and H's, so a very stable compound is ammonia. We have C's and O's, so a very stable compound is CO2, and we also could produce some O2. You can balance this simply by putting a 2 here. That gives us, this is actually not O2, another very stable compound. Could be H2O. That does balance it. We get the 6 H's there and the 2 there. So classify this reaction. You can call this a lot of different things, but one thing is breaking up into 3. Call that decomposition. So again, this is huge. When things are heated, they decompose. Okay? Things are heated, they decompose. They do not necessarily, it's not burning. It's not the same thing. Burning would be what you would see in lithium's burned in air, or a combustion reaction where you're adding oxygen or whatever substance it's being burned in. In this case, it's just heated. Separate them into the most logical elements that you see. Chlorates separate into chlorides and oxygen. Compounds, binary compounds, separate into their atoms. Ammonium carbonate is going to separate into ammonia, carbon dioxide, and water. Three very stable compounds. A solution of hydrogen peroxide is catalytically decomposed. So I'm going to do this one again to talk about decomposition. Hydrogen peroxide is H2O2. Where that comes from is hydrogen, which is plus 1 in its charge, and O2 minus 2, and this is called peroxide. And this is actually taped on the door of room 206. So that's the peroxide ion, so we get H2O2. It's decomposed. Okay, so probably was heated. Let's think of some logical choices for it to break into. We could break it into H2 gas and O2 gas, but H2 is really combustible, so that's not a stable thing for it to break into. Okay, we could have it break into H2 and water. Okay, water's great. Again, there's hydrogen. We don't want to create hydrogen, so we could break it into H2O. All right, that's fine, and O2. That's also very good. Balance this reaction. Give it a 2 here and a 2 here. That should take care of it. Catalytically decomposed. Name the element being reduced and the element being oxidized. Before I do that, again, hydrogen peroxide came from this ion peroxide, and it broke into the two most stable compounds, H2O and O2. The element being reduced and the element being oxidized. Well, we got to go through here and we got to label the charge on each element. We know that hydrogen's always plus 1 and hydrogen's always plus 1. So really, there's only one other element left, and that's oxygen. So we have to choose oxygen as the choice by default. And the deal is, oxygen is going from, actually O2 minus 2, each O is minus 1 in order to get to that state. So it's going from that to O2 minus 2. Minus 1 to minus 2, it's being reduced. And it's also going from O2 minus 2 to O2 0. This is reduced. This is oxidized. Kind of a complicated thing, but by default, the only possible choice for that is oxygen. A solution of potassium iodide is electrolyzed. All right, solution, so K plus I minus. We do see some ions. It's electrolyzed, and what electrolyzed really means is it's got to be put in water. We do see water there, and for it to be electrolyzed, it's really going to be breaking up into its ions. Actually, you know what? We don't have as much time left, so I'm going to go over this one in the next video. This will be on vodcast number 3. Take care.